Hello, my name is Nicholas Alt from the Technical University in Munich, and I want to present a system we built up for haptic exploration of a room for navigation tasks. So the scenario we are looking at is depicted on this slide here. We have a Turtlebot-like robot, or like one of those vacuum cleaners, and those robots need to navigate in an office scene or a household scene as shown over there. And you see that there are all those objects in the way which are seen as obstacles on a visual sensor. So we thought, what's the minimum amount of information we need from haptic modality to be able to manipulate these objects? And what we came up with is something we refer to as haptic tags. It's basic haptic properties of objects on a per object level. And we want our robot to explore these haptic tags and then do navigation decisions. So basically what we do, we poke each of the objects and watch with the camera what happens. And the interesting thing is that the camera watches both the reaction of a deformable sensor and the object itself. So from one sensor, from the camera, we get sensor data. We only need a passive mechanic sensor for that because we measure it with the camera and we see what the object does. Can we have the video now? And I want to show you a little video which which shows our system in action. You want it from the beginning? Yeah. All right, we'll first see a quick view of the system itself. So the important parts we have here is the webcam, which, as you can see, watches the scene, the object, and the sensor with templates on it. Now, if we have a vision-only system, we would have a situation like this, that a navigation path is blocked on a visual level, so we decide to explore these objects haptically. And you see now that the camera tracks both the sensor, that's the template on the bottom, and the object itself, and measures the force of the pushing force and measures how the floor moves. And as all of these data come from a single video frame, we know that our measurements are naturally coherent, and we do not have to synchronize any external haptic sensor or with vision. We end up with these haptic tags, which show us, for instance, if objects are stable. And based on these tags, we can make navigation decisions and, for instance, move the object away here. Thank you.
Okay, thank you. My name is Thomas Andersen. I'm from the Technical University of Denmark, and I would like to talk to you about the next generation universal robot driver for ROS and ROS Industrial that we're working on. Just so you know, this is the universal robot. Next slide. The problem with the current universal robot package is that the robot side driver is written in UR script, which is their own language, so it makes it a bit difficult to add new features. Another, especially main problem is that the control rate is only 50 Hertz, even though the control on the robot runs at 125 Hertz. So this means that we can't, first of all, move very fast if we want to do something like visual turboing, and also that there is a bit of delay, almost 200 milliseconds from we command the position until the robot gets there. If we try to increase the transmission rate, this is what happens. So the UR script can't read data fast enough from the socket. Another problem is that it doesn't support velocity commands, and it's a standalone package, meaning that we have to have a dedicated person to maintain it. What we're working on, the next generation driver, is written in C, which makes control rate limited by only the robot and the network, of course. So this means that we get much faster response, even at 125 Hertz. Actually, we only have a delay measured with my computer for 17 milliseconds. It's easily expandable with new features as long as you know how to program in C. And we're going to do it using the industrial robot client, which makes maintenance much easier, as if there is a problem with the driver that gets fixed for the ABB robot, for instance, it will also work for the universal robot. Also, we get the velocity-based control from that. And yeah, the maintenance, I just mentioned that, and it's forward compatible with any changes that you see in ROS Industrial. So that's about it. If you have any questions or want to participate, have any ideas if you're using the the universal robot, please contact me or some of the other guys working on it here from Fraunhofer or Georgia Tech. And we're also going to have a Birds of a Feather session tomorrow at lunch at 1 o'clock next to the robot at work and Fraunhofer stand outside. Okay.
Did you get the page?
Yep.
Okay. Hi, my name is Giampiero Campa from MathWorks, and I wrote this page last year, actually following Brian's suggestion, and together with Antonio Franchi and Martin Rieder, MPI, basically for two reasons. First, to provide a mailing list for the user interested in the topic, and second, to try to answer some question I was receiving left and right about this. Can you scroll down? So here are the interfaces that exist so far. IPC Bridge is the first one. It can be slow sometimes, depending on what you're trying to do, but it's certainly reliable, has been there for a while. Java MATLAB Bridge, this really is based on some packages, actually ROS Java files which have been repackaged so that they can be called for MATLAB. I heard great things about this, seems to be working really well and allow a much deeper level of integration between MATLAB and ROS Java, something like code generation and stuff. So other kind of approaches will be try to call ROS C API from MATLAB, from Maxfile. This will be the fastest way to do stuff like simulation. It's not straightforward because MATLAB and ROS rely on different versions of the Boost library, but nevertheless, people have done it, like Ed Kazupsi at USC and Jan Meyer at TU Darmstadt, like, for example, using CMake. So these are the interfaces that exist out there. Then there is a way to read ROS bugs in MATLAB, that's interface. That's a library. Number 4 is really me speculating about other possible things you can do and how. Stuff that is not there yet to go down. So two last points. First, use cases, requirements. If you have any comments, opinion, use cases, I definitely want to hear about you. So please send me an email, send an email to my mailing list. Second, we are actually hiring. I want to hire someone that will worry about developing an interface with ROS, among other things. So also in that case, please let me know. Thanks.
Hi, my name is Alex Buival. I would like to tell about our project in which we equipped our drone with ultrasonic ranger connected via Arduino and sent the data to ROS. Next. First of all, we connected up an ultrasonic sensor to the Arduino and developed a simple Arduino sketch which reads data from sensors and sends it to USB. Next. Second, we connected the Arduino to our drone by onboard USB and developed the program that reads data from USB and sends it to network socket. This program runs on the drone. Next slide. Third, we took the ROS driver by Autonomy Lab and added the module that reads data from socket and publishes it to ROS topic. We are going to use this upgraded drone in the first Russian competition of flying robots by company Krog. I would like to underline that the Arduino to ROS connection I told about is finished and works. That is shown in the next video. Next slide. Oh, no. Thank you.
Oh, I was wondering where the next person was.
Yeah, would the next presenter please hurry up to the stage? Where are you? Okay, so normally these lightning talks are a mixture between shameless plugs for products and, you know, deep technical work that other people have done. This is going to fall into the shameless plug. So we used to be called Heartland Robotics. We're now called Rethink Robotics, which we all think is a great new name. It is a good name. But we are, in the last week or so, we've announced support for a Baxter research robot, which is basically a ROS interface to the Baxter manufacturing robot. Same hardware, different software stack. It's been in alpha for the last 2 months or so and is just going into beta. That means it's becoming more publicly available. Basically, you get the robot, you get some custom code on the actual robot itself, which runs all the robot joints and reads the sensors, and you access it by using a machine that's connected over the network. So you communicating over ROS between the two machines. We have documentation and sample code on GitHub, it's the trendy place to put it, and we have a forum for people to work with another. This is the astonishing low price of $22,000. So see if you can get 2 7-degree of freedom arms, a pan tilt head, etc., for that amount of money. So there is no warranty. What would you expect for $22,000? But you can purchase a service plan, and then I guess the only kicker, given the location we are, is that this is now available in the US, but not currently in Europe, but we're working on that. So what do you get for your $22,000? Well, you get an awful lot. You get 2 7-degree of freedom arms with torque, position, and velocity sensing at each of the joints. You get 2 cameras, one on the end of each arm. There's a 3rd camera in the head. You get, the head can pan, and it can nod slightly. You can purchase different types of end effector which plug into the end piece. There's a sonar system which is like a sort of poor man's sort of rangefinder on the head. Each of the arms have rangefinders also. Anything I missed, Chris? Okay.
40 seconds.
And we have been working with these 3 different alpha universities in the US, and as I said before, the beta is now open, and you can visit our demo. It's just outside that door. Thank you very much.
Okay, hello everyone. So I'm Hugo from the Shadow Robot Company, and I'm here to do a shameless plug as well. So talk about the new product which is called RONEX. You good? Yeah. So what does RONEX stand for? It stands for Robot Nervous System. What's the principle? We have, when you build a robot, you have actuators, you have sensors, you have lots of hardware. You want to make a nice robot, and you also normally want to talk to your computer to get your algorithm running, etc. What we build is the part which communicates between the actuator, the sensors, and the robot. So this is the green thing you can see on the screen between the robot. We also want it to be easy to use. We want it to be plug and play, and we want to use ROS because we love ROS. That's why we're here. So it's basically a plug and play robot nervous system where you plug in your actuators, you plug it into your computer, and you get all the data on ROS. Okay, so how does it, previous, sorry, it's okay. Yeah, so how does it work? It's based on EtherCAT. Yeah, no. Based on EtherCAT, so you can plug it into your network card. You get, yeah, weird. Anyway, it's fine. Thanks. You get a 1 kilohertz real-time control loop. That means that you can run your controllers directly on your computer, which is very nice for prototyping. You have a bridge which ensures this communication, but under this bridge you can stack up to 5 modules. And these modules can be configured for your own needs, so you can build them for your custom needs. You can ask us to build a module with different input, outputs, etc. And the last point here is that you can also have an EtherCAT out module, which makes it possible to chain load lots of different RONEXs. So you can get more than those 5 modules, you can get hundreds of them, as long as you are under the 100 megabit per second rate limit on your bus. So that's it. So for more information, you can either come to me or go to our website. Thank you.
Hello, I'm Oliver Kurz from Fraunhofer IES. That's not the Fraunhofer Institute here in Stuttgart, but in Nuremberg. Let's talk about outdoor robotics, and I bluntly state here that for outdoor robotics everybody uses GPS. Or in more generic terms, I want to talk about GNSS, that is Global Navigation Satellite System, because besides of GPS there's also the Russian system GLONASS, and then there's the European Galileo system coming up, and more. And my recommendation is to use RTK for better accuracy when you want to use GPS positioning. We conducted a project and we used a UGV platform. That's an outdoor RC car chassis with Ackermann steering, controlled by ROS planning. It has a low power PC Panda board, and on that we implemented a low-cost GPS receiver connected to a base station, and we used a GPS RTK solution for positioning. The RTK base station was connected over Wi-Fi TCP connection. To go into a bit more detail, next slide please. There you can see a comparison on the left-hand side. Figure is the same data set processed with single positioning GPS. That's the blue points where you can roughly see the accuracy is in the range of some meters. And the grid size is 2 meters here. And the green line, that's the RTK solution that you can get. That's in a centimeter accuracy range. So you can clearly see where the rover went over the path. We used, for that, we concentrated to use low-cost GPS receivers. So we used GPS L1 Skytrack receivers for both base station and the rover. They are about 60 euros. The antenna was a bit more expensive. We used like a 100 euro antenna for on the rover, and on the base station 200 euros, you can see. We use the RTK Lib open source software, and this is something which is a really great open source product. And we conducted the RTK solution inside RTK Lib, and then from there, next slide please, we could provide the global position reference information as a coordinate transform in ROS. The planning of the robot itself was done in the local odometry frame, and then of course you would have some odometry drift, especially with low-cost sensors, and for that we used the GPS measurements only if the quality is good enough for a solution to really correct this by a coordinate transform, and then we received really good performance in a range of centimeters for control and a few degrees for orientation estimation. Thank you.
You can start with the video. Hello, my name is Luca Lattanzi. I'm from an Italian company. We are system integrators, and the name is Loccioni. In these 3 minutes, I would like to show you our first attempt to use ROS in real industrial environments. We are system integrators. We develop quality control systems, also based on robotics. So our main competence is to measure. In this project, we try to apply the sensors and the measurement system on a mobile robot with a manipulator, so that we can have a mobile system that is able to autonomously navigate in its environment, detect the products that have to be inspected, and then to perform functional tests. As a validation scenario, we have chosen the household appliances, in particular washing machines, because washing machine is one of the market sectors in which we are working. And so the robot is able to move in the environment and detect obstacles and collision, is able to interact with the product, and is able to measure. It can acquire images from the washing machine, for example, is able to perform simple tasks like pushing buttons, is able to perform measurements, like for example acquiring vibration of the external cabinet of the washing machine, or acquiring noise from the product, and is able to perform more complex tasks like opening doors or like turning knobs. So all the tasks that are required for the proper inspection of the washing machine. The control system is based on ROS, and to be honest, is a hybrid system. Is mainly based on ROS for for controlling the robotic hardware, but also on LabVIEW. It is a graphical programming language for acquiring measurements and from sensors. So thank you for your attention. That's all.
Okay, hi all. I'm Zdeněk Materna from the BU team, and I would like to present a solution which we have developed within the SRS project. It can be, or it's a solution which can be used for telemanipulation in cases when some autonomous solution fail. So it offers a complete pipeline for telemanipulation, also including the grasping. Well, it's based, it uses ROS, it's based on the functionality of arm navigation stack, and it offers collision-free arm planning. And for this collision-free planning, it uses our 3D environment model, which is based on the Octomap. On the right side of the slide, you can see it's RVIS plugin. It's the user interface for this telemanipulation. There are just a few buttons, and it was designed to be very easy to use. It's for the non-expert users. Well, as I said, it should be, or it's designed to be simple and easy to use and intuitive. For better depth perception. We have patched iris, so now we have stereoscopic display, and another cool feature is the usage of the 6D of mouse, a space navigator, which can be used to set the goal position of the arm. Well, on the picture on the right side, you see the robot and the marker representing the desired position, the goal position. And the cool thing is you can use the space navigator to set this goal position, and it's not the goal position, or if you are making changes in the goal position, it's not done in the robot perspective or in the robot coordinate system. It's converted, yeah, according to the position of the virtual camera in the iris, so it's very intuitive. Well, and as I said, it's complete pipeline, so, well, I will continue here. Well, this solution, we call it assisted arm navigation, has been extensively tested during a large user study. We had 60 users, and the results are coming soon. We will publish something. There were more experiments. One of them was comparison of the stereo and the non-stereo. And we are also going to compare simulation and the real experiments. Well, currently it works with the ROS Electric. We are going to update it for Groovy. Yeah. Okay.
Take it that way. Thank you.
Hi, my name is Markus Liepert. I'm from Eugene Robot, and I'm going to talk about a small project we're doing. Not that one. Okay, so it's called Motion Retargeting Pipeline. Yes, this one. Okay, so it started over 2 years ago at PAL Robotics. Next slide, please. And there we used it with the REAM to do online motion retargeting for upper body teleoperation. So the upper body of REAM has 18 degrees of freedom. And well, that worked nicely. And the future intended use already back then was to do motion recording for content creation and also eventually motion teaching for motion learning. Next slide. So the goals were similar human motion should result in similar robot motion. That's not trivial since, well, there are different humans, like in size, and there are also different robots. And why is it called retargeting and not mapping? It's not a precise definition, but retargeting is often used to emphasize that motion mapping is happening between significantly different kinematic structures. And what it basically does is that it takes in the input motion, adapts it using body proportions of the human operator and also the robot operator. And then it does inverse kinematics to transform that adapted end poses like hands and wrists and head to compute joint positions for motion control. Next slide. And at PAL Robotics, they have been developing further and further. For example, we use the OpenNI tracker for the input motion, which doesn't have any information about head and hands orientation. So they integrated IMU data for that. And now we started to use it again at Eugene Robot. It's part of 1 minute, okay, at the RosCon project, where we use it with a different robot. And we already added motion recording and motion replay, and there are a couple of future projects we want to do. And now I stop that to move on to videos, to show you some snippets, which is more interesting than me talking here. So first you will see the REAM from PAL Robotics doing motion retargeting. So yeah, that's me on the left, and REAM on the right, basically doing what I do. And there you see my supervisor, Adolfo. So that's basically proof that it works with different operators. That one is nice. And yeah, so the motion looks quite similar, and you see we're using different motions. There was also a nice video. Done? Okay, thanks.
So, hi, I am Martino Migliavacca from Politecnico di Milano in Italy, and I'm working on R2P, which stands for Rapid Robot Prototyping. And basically, it is a framework composed by hardware and software embedded components, which implements the basic functionalities we usually need to prototype a robotic application. And so we can choose the modules we need and control a robotic platform without the hassle and efforts that we usually have to face when we have to build a robot from scratch. It's open source from both the hardware and software point of view, and basically we have the same ROS goal, I can say, but applied to the hardware level. And the boards are connected through a CAN bus protocol, which we need for real-time performance. And the users use a lightweight publish-subscribe middleware. We choose to follow a ROS-like API, so people who is used to ROS should be learn fast how to use R2P. And thanks to MicroROS node, which will be presented tomorrow, their nodes in R2P are also exported to ROS, so we can interface with hardware components directly from the ROS application. And in the next slide, we can see a set of hardware modules that we already developed. We have the basic functionalities of common applications like motor control, sensors, or inertial measurement unit, a power supply, and we are also developing much more modules. And as it's an open source project, we hope that many other will come. So, thanks.
Hi, my name's Paul Bouchier. I want to say a few words and ask you to help us figure out what the right answer is concerning ROS and real-time. So there are ROS, we all love ROS, that's why we're here, and it's being incorporated into products. We're seeing multiple products described here, but something about commercial products. Well, the question is, where should ROS go next? Commercial products is one possibility, but commercial products, commercial robots often need real-time performance. So I've got a definition here, slightly different than the gentleman from BMW cited. It is frequency rate agnostic. If the system fails, then it's considered to need hard real-time. So ROS has many packages that bring great value, but the question is, and the question I'm asking you is, should they be enhanced to provide timing guarantees? And here are some examples of ROS packages that clearly relate to time and to the robot motion and adaptation as time goes on. Next slide. So the state of the art today is that real-time subsystems are deployed in external non-ROS processing systems. And we've got some examples, and people will be describing ROS-C and UROS tomorrow, micro-ROS tomorrow. But basically, the real-time system is given real-time responsibility. The consequence of that is that ROS packages can't be in the loop, in the real-time control loop, and provide hard real-time guarantees. Or you have to run the system slowly enough that Linux can provide those. Next slide, please. So this is an idea for an approach. We could perhaps select an RTOS if ROS supported POSIX, if a POSIX interface was enough for ROS to run, then perhaps there are several RTOSs that do offer POSIX interfaces. However, to make real-time work, you really have to make the whole stack guarantee real-time performance. And so therefore you'd have to also go up through the layers into the middleware and into selected packages and assure that they could guarantee real-time support. There's been some discussion of using Xenomai and Yocto or Yocto as real-time infrastructures. The key question that you have to ask is, how strong a guarantee can they make? And that's a critical question. What will you or will your project manager give you permission to do that? So I've got a survey there, real-time ROS. Look at it. Tell us what you think.
Hi, my name is Martin Günther. Today I'm just going to give a very quick teaser for the integration of the ARM navigation pipeline on the Neuronics Katana arms. This is the Katana on our Cortana robot here. So we couldn't afford a PR2, that's why we bought a Katana. And the Katana arms, they all have 5 degrees of freedom. There are several variants. This one has an angled gripper. There are also ones with a straight gripper. And the Katana driver stack is actually a nice, clean ROS wrapper around the horrible API which comes with the ARM. And it provides a followed joint trajectory action, publishes joint states and so on. It's got a URDF description and full simulation of the robot in Gazebo. Next slide. You can basically plug it into, it provides everything you need to plug it into Move It or into ARM navigation. And then there's more stacks, the Katana manipulation and Cortana robot stacks, which configure the ARM navigation pipeline and the object manipulation pipeline for our robot. And we are not supporting Groovy and Hydro yet. We're also not yet using Move It, but I started configuring it today and I'm halfway done, so it's really easy. And so if you have a Katana ARM, and you're using our package or you're not using our package, please come and see me. I'd like to support all the types of Katana arms there are. So yeah, that's it. Thanks.
All right, Bill Smart from Oregon State University. As Brian mentioned earlier this morning, Oregon State is going to be helping out with some of the hosting of some elements of the infrastructure. Specifically the wiki, answers, and packages. Next slide, please. So in the short term, what we're going to do is just move everything to Oregon State. You will not notice any change except much better uptime and much, much better uptime. In the long term, what we're hoping to do is to work on some of the elements of the infrastructure, make it a little better, fix some of the problems that have come with scaling. The wiki search isn't as good as it used to be because it has to search over more stuff. Next slide. But we want to know what to work on. So please email me, tell me what you'd like us to work on. We'll put that into a priority list and we'll try and make things better. Thank you.